Welcome back, everyone. We are at week 5. Um, we are going to be discussing traversing and all the fun details about traversing and the theories. I know for the majority of you, it's going to be a recap, but the great thing about recaps is you guys get to pick up on things maybe that you missed the first time we went through these stuff, or maybe just a good recap or just a good refresher for everybody when they're going through everything from the first time we got introduced to it. Okay, again, if you're my online students, you guys, off campus, I guess I should say, you guys probably do a lot more with the traversing calculations on the digital side of the world. So maybe if you have like a Trimble Business Center, or you run through it on AutoCAD or anything like that, it's pretty automated. But again, it's always good to remember just the very basics, with traversing computations. But before we get into any of the computation part, we just got to discuss what is a traverse, right? And the traverse part, and let me pull up the book here just to get the definition. Uh, there it is. Move you out of the way. Back again. So I got. Let's just go to the just a short little definition here, right? I was going through there. Sorry, guys. So traversing. That is the method used in observing angles and directions of a traverse line vary, right? So these are the subsections of it. Let's just find nice, easy traverse computations. That's going to be second part. Oh, no, they don't have dang it. All right, here we go. So interior traverse angles used for many types of work, but they're especially convenient for property surveys. Although interior angles could be observed by either clockwise or counterclockwise to reduce mistakes in reading and recording and computating, they should always be turned clockwise from backside stations to foresight station. We'll show you an example there. And they're going to talk about deflection angles. They'll talk about kind of stationing, that good stuff, and then running into the direct and reverse readings to computate for your distances and angles. Um, so I got a quick slideshow for you guys. So again, it's a series of straight lines connecting successive points along a route of a survey. It's pretty basic, but the other portion of a traverse that needs to be addressed is these points are fixed points, right? So once you run a traverse and you make the adjustments with those traverse, so again, let's say we start here at this northeast corner, we run clockwise through this thing, setting up over every point, backsighting, then foresighting as we go along. We close back onto this by, this would be our slash setup here, backsight to this point here, and then foresight to here, and that would be our closure. And again, we would get a raw misclosure. Using that raw data, we would then use what we call the compass rule adjustment for a lot of you guys. And this is just all recap. It's the compass rule adjustment. And then we would run through the series of corrections for each one of these points. And let's say we're working on a construction site through this area inside here. Well, now these points, when we run through that adjustment and get the misclosure down to basically 0, these become fixed points, immovable, right? We cannot move these points anymore. That once we run through the calculations, we figure out our misclosure, and we get the misclosure ratio over 1 in 10,000. That becomes the now new control for that project. So purposes of the survey, we have boundary surveys, right? We can do boundary surveys with this. So an example of a plat here, this is a big parcel here. So this is this bigger 1197 acres. So I'm running through this highlighted through here. This is the property that was done for it. And again, most likely they ran a traverse for this entire huge property. Could they go from this point to this point directly? Depending on the area, if it's flat ground. But sometimes they had to run a series of just turning points through, kind of, similar to turning points, but establishing other control points to find these property corners. as they went along, especially this line. But again, if they were to locate these property corners in between, they were able to use those as their also kind of controlling part. Other portions, we can use it for horizontal and vertical topography. So in our office, a quick example that we did, actually, let me just pull it up, find it on. I use this example a lot because it's still very, it's still ongoing. This was the case. So I'll pull up Klamath Falls here. I'm gonna pull up the airport. So currently, there's two phases going on with all this concrete work, or was. There's only one phase going on, but all this concrete work that you see through here and here, these are where the F-16, the military base is at. So all this concrete has been replaced here, basically with this little, you can see kind of this line that's running through there. In case it was in two phases. This concrete got replaced first. All of this, certain specs and tolerances had to be met. And now currently the second part is all this right here, all this concrete that's through here, right? And initially they required, a topographic survey of the entire thing. And so we had to go out there and set control, came off of we set two control points off this, to initially start with GNSS. And then we traversed around this entire thing on the outskirts of it, out here, all the way out to here. I think we went up. Yep, we went up. I believe we went through here, up through here, and then came back around and closed back onto ourselves in this area. And then we had to run through the adjustment to make sure that the raw mesh closure was good. There was intolerance, and then we had to run an adjustment through these points that we ran through to get a closed traverse or an adjusted traverse for this entire project. Once we got that traverse down and we got the control down, we started the topographic survey. And again, the topographic survey had to be really tight, the control had to be really tight in order to have really good data for the topographic survey, horizontally and vertically. I don't know if you can tell here. Can't really tell on this because it's too it's not defined enough. Oh, actually, you can kind of see it here. So these concrete right here are, they cut them out 20 by 20 panels for the majority of them. Some of them are a little shorter, like these ones are a little smaller. We had to physically go and tie every single one of these little panels, every single one of these corners, every single one. So you imagine the location was important horizontally, but as well as you had to be physically or vertically had to be really well too, because you had to figure out where this was all draining to, right? If we had, because there's a serious catch base, catch basins that run along here. There's someone that run, I believe, up through here, through this middle part. There's a series of catch basins, and it all runs on to the east, and it runs down all the way through here, across, and it comes out in this little canal area over here. But we got to make sure that it's all draining right away from the base. So vertically and horizontally, we had to be really, really tight on this project. And we're still growing. I was just out there last week. We're just about finishing up this project, but hopefully we'll be done soon with this entire thing. But that is, one of the examples of why you need a traverse running horizontally and vertically control for the topography. And again, currently we're in the construction phase of that. And again, this is an example of mishaps. I have just an example of mishaps when we don't predetermine the locations, when we just build without, understanding where this actually is going to fall. So this is why we do these type of traverses. Again, another mishap of just not knowing, not getting good vertical data for a house. And you see the driveway run, that is not legal whatsoever. Again, same thing, not knowing where, move that on accident, not knowing, where the location of utilities are going to be compared to the actual layout of the houses, of the lots. That's not the best. And then, just simple mishaps of, this is just a vertical mishap, maybe not understanding the actual elevation difference between this and that, between the ground and your machine there, the LATM. The other part that we can use is aerial mapping projects. So again, aerial mapping projects, I'm sure you guys seen those marks, especially on the pavement, those big white like X's or crosses. Those are aerial markings. Those are laid out to get photogrammetry, the photogrammic planes run through there. You run through a series of traverse, and then you can establish your horizontal and vertical control. You give that data to, you give all that data to who's ever running, whatever company is running these aerial photographies, and they can build, you know, this photogrammetry aerial mapping based off of those measurements. There's two types of traverses. There's the closed loops, as you can see here, and that's what we've been running a lot. And there's the open loops. So I think last year we discussed with the open loops, there is two types of open loops where you don't, where it's linked or unlinked, I think. So in this example, you would have two known control points that you come off of, right? Two known, whether they're like NGS benchmarks or maybe you set them themselves with GNSS receivers, based on the coordinate world. And then again, you have two benchmarks that you close on that are known coordinates of benchmarks that you close on. And then you run through your traverse as such, and then you come back to. And again, I'm going to show you another example that I did that way. And that's up here on, right here on El Dorado. Sorry, I'm getting lost. So El Dorado, I don't know if you guys have driven through there, but it's all different. Well, I'm sure for you guys, you don't really know what it used to look like. See if it's updated at all. So this is not. Where did they update? They updated over here. So all this is new concrete. All this is new sidewalk, as you can tell. All that is new sidewalk. So again, I had to do a traverse starting on this western end of El Dorado and traverse, or do it not traverse, sorry, do a topographic survey through this whole thing, all the way down to, was it Van Ness or Lowell? I can't remember. I believe it was, oh no, it was over here past Lowell, actually. It was about to Lowell over here. So I had to establish, before I started my traverse or started my topographic survey, I had to establish my traverse first. And I wasn't going to, start here, go all the way through, and then come back all the way up. I wasn't going to do that because I was going to be inefficient. So what I did is I established two control points down here with my GNSS. And then I came down here and I established two more control points right here to close on, right? So then before I started any topographic survey, I came here, set up my instrument, backsighted, and then I would set my control as I would run down this entire thing, establishing control through this whole thing. And then I got to here, and then I closed back onto myself, and then raw data was good. And then after we got the raw data down for control, back to the office we went and made the adjustments in the office, and it was control that was good to go for the remainder of the project. And so we did it. So again, then I spent the next week or so just just topographic surveying this entire right of way, this entire street, into right of way to right of way on El Dorado, and then getting all that data to the engineer so they could build their new development. So that is closed and open. And again, the other part of open that's not mathematically and it's not advised, it's not recommended. It's just starting with two known control points, and then you would traverse down, but you would end with two unknown control points or two unknown benchmarks. And that is not practice. That is not the correct way to do any of this. So these are the two methods. You start and end on the same point, right, on the closed loop. Or if you start on an open loop, you have to have at least four known benchmarks. One to back. You start here, back site, you establish control points, and then you end on your other two known benchmarks. And again, traverse equipment, well, back before we had, any of the fancy equipment, you had singular. So singular equipment that could only do one function. So this was like a theodolite that could just measure angles, right? Uh, you just another transit to measure angles, and then you would have some kind of distance measuring, whether it be in this tape. This is just visually, but previously, before any electric measurements came out, there was chains, there was steel tapes. Those were the methods that they would use for measuring distances. The chain, remember, is one chain equals 66 feet. And then starting in, late 70s, early 80s, comes the invention of the total station. And that revolutionized pretty much, that started the revolution of slant surveying with technology, right? Nowadays, total stations are just, the go-to. That's the basic survey equipment that everybody uses because it does everything. It does your angle measurements, it does your leveling, it does your verticals, it can calculate any of those methods that you guys have just done one thing at a time. And again, the reason we do that is just to remind you and keep you guys up to or informed of all the methods of how surveying can be accomplished. But leading up to that is this other side of it, the other side of the world where it's total stations and GPSs and now drones. And that's where we're going to. And again, photogrammetry, all the good fancy tools. This is just the very basics to get you back started in that world. And again, traverse computations, close computations, solve the random errors in the survey, create the math model of the polygon, right? And again, that math model becomes, once you close it, it becomes the fixed and immovable control points for you. So again, another recap is we got step one, balance the angles. So again, you're going to have the summation of your interior angles, and that's always going to be n minus 2, right? So in this case, you had 6 interior angles, 1, 2, 3, 4, 5, and 6. So, oh, sorry, I skipped one. That's what it was. Sorry. So step one, balance the angles. It's the summation of the interior angles is n minus 2 times 180, n being the number of interior angles. And then we step down here. So we had 6 angles. So the n minus, so then we have 6 angles. So that's 6 minus 2 times 180 equals 720. So your closure should be, that's your standard right there. 720 is where you want to meet. Quick example or example of that is let's say you measure your interior angles from the field data and you get 726. So that means 726 minus 726, 6 degrees right there, 6 degrees that you went over. So now if you go your 6 degrees divided by the number of stations that you have, that is 1 degree per station correction, right? And that also applies to minutes and seconds. So just go back through your 161 notes and verify, that, you just remember those steps, and we'll go on to step 2 here. So again, we'll calculate the azimuths of the sides of the traverse. So again, depending on the project itself, if it's actually in the real, if you're actually doing, coming off of GNSS coordinates, your northing is going to be most likely the correct way. If you're using just a total station, and you're just setting it to 0, well, then your north or your 0 is going to be set to wherever you set your 0. Step 3, we're going to calculate the latitudes and departures. So remember, latitude or departure is your length times your sine of the azimuth, and your latitude is your length times the cosine of the azimuth. So latitude moves in the x fashion or the xy, and then latitude is the y, right? Hang on, did I grab the right one? Oh, I did not. Oh, it is the right one. I'm sorry. Sorry, I have 2 sessions going on. Okay, there we go. Sorry. I'm sorry, guys. So again, that is calculating the latitude and departure. And then again, so in this example, using, we consider the unbalanced latitude and departures, because we would then need to balance the latitude and departures. So if we had, let's see, step 3, yeah. So if we had, our measurements, we would take those measurements and just note them down as such. And so we would have, here's our latitude, here's our raw departure from 1 to 2, from 2 to 3. Here's our latitude raw, here's our departure raw, right? Writing those things down. And you get those stations, or you get that data down, and then we have to figure out the linear error of closure. So again, the linear error of closure is your latitude, the summation of your latitude squared plus the summation of your departure squared all over the square root. All right. And so that would figure out your linear error of closure. And again, departure moves in the X fashion, and your Y moves in the or your latitude moves in the Y fashion. So that would be, your point here, and then your point here, and this is your linear error here for each point. Or that'd be like, let's say this is your starting point here. Keeps moving. This is your starting point here in this location. This is your starting point, and this was your closing point. Well, now you got to figure out what was the linear error of closure. This guy right here, this black line that's running through there, right? So the relative closure, your ratio is the standard that you have to meet. The minimum is 1 in 10,000. Anything over 1 in 10,000, and again, in the state of Oregon, the ORS states that your closure has to be minimum 1 in 10,000. So again, you started, now this time, let's still go counterclockwise. You started at A here, ran through your stuff, right? And then when you calculated your linear error of closure, that ratio has to be greater than 1 in 10,000. And then step 5 is to adjust the traverse, make the math model. And again, solve for the random errors. And everybody's used to using the compass rule. And that's what we're going to be doing. The Crandall rule and the transit rule, those are kind of outdated. And then least squares, well, you will learn that in least squares and using the software called StarNet. And you guys will have a great time with that one, I promise. So the transit rule is angular accuracy is much higher than the linear accuracy. That's just that one. Let's see. But so step 5, or sorry, adjust the traverse and to track the transit rule. So correction to the departure is the absolute value of your departure times the sum of your departure divided by the total summation, and you get the absolute value of departure. And then the same thing applies for your latitude. The Crandall is the poor man's, right? What we call the poor man's. It's least square. It's the angular accuracy is higher, much higher than the linear. The weighted observations based upon standard error of the observations. And again, you will learn all about that in least squares. And then we have our compass rule, the AKA Bowditch rule. Angular accuracy and linear accuracy are near the same. So this is why we use the compass rule adjustment, because both are balanced, very close to each other. So again, step 6 would be calculate the coordinates. Step 7, calculate the area. Step 8, calculate adjusted bearing distances. And that would be the tangent of your azimuth over the deltas of your easting over the deltas of your northing. And then your distance is your deltas of easting squared minus your deltas northing squared all over square root. So I'm going to post a couple videos from Pearson. And they do another great example, or a great job of discussing. I'm going to post this video. Where are we at? Field notes, angular misclosure. Oh, right there. So this video here, this angular misclosure, I'm going to post that on the YouTube page just to give you guys another recap. And that way you guys just remember what we're looking for with the meat and potatoes of traverse closures. All right, I'm going to stop this one for now, and I'll post another video of sessions 2. But again, make sure you watch these Pearson videos. They're very great. They're very good at explaining just the very fundamentals of the topic that we're talking about. All right, guys. So that's where I will pause everything, and then we'll talk to you soon on the next one.